Welcome, curious minds, to the deep dive. Today we're casting our gaze far, far beyond our familiar blue planet, out into, well, the cosmic abyss. Imagine, if you will, the sheer, almost unimaginable scale of the universe. We're talking billions upon billions of galaxies.
Each one just packed with hundreds of billions of stars. The numbers are staggering.
And around each of those stars, we now know, planets are likely orbiting just countless worlds spinning through the void.
It seems almost inevitable, doesn't it? The possibilities for life, for intelligent life,
Yeah.
they feel, well, truly infinite based on those numbers alone.
You'd think it should be a bustling cosmic neighborhood, right? Full of chatter, activity, maybe advanced civilizations reaching out across the void.
But then there's this profound question that arises. What if it's not like that at all?
Yeah, what if, despite all that vastness, all that potential, all that cosmic time, the universe remains profoundly, unsettlingly silent?
That profound quiet, that cosmic silence, that's precisely what brings us to today's deep dive. We're tackling one of science's most enduring and, frankly, one of its most absolutely fascinating mysteries, the Fermi Paradox.
The Fermi Paradox, okay.
It's a question that really challenges our fundamental understanding of who we are and, where we stand in the grand scheme of things.
And that's exactly what we're here to try and unravel. The Fermi Paradox, at its very core, is this mind-bending contradiction. On one hand, statistically, the universe should be teeming with intelligent, technologically advanced civilizations.
The sheer numbers, as we'll get into, they're just incredible, really hard to wrap your head around.
Yet on the other hand, despite decades, literally decades of searching with our best instruments, we have absolutely no conclusive, verifiable evidence that they exist.
None. Zero. Zilch.
It's not just a little puzzle, is it? It's this profound discrepancy in how we think the cosmos works.
Exactly. It directly challenges a foundational scientific assumption, something often called the principle of mediocrity or the Copernican principle.
Can you explain that principle a bit more?
Sure. It basically suggests that Earth isn't special, that our planet, our solar system, even our galaxy, they aren't unique or privileged in any way. And therefore, the processes that led to complex life here should, logically, be pretty common elsewhere in the universe. Life shouldn't be a fluke.
But the Fermi Paradox slams right into that, doesn't it?
Yeah.
It forces us to critically reevaluate that whole idea.
It absolutely does. It takes what seems like a simple observation, hey, we don't hear any alien radio shows, and elevates it into this profound philosophical and scientific dilemma.
It makes us question humanity's unique position, or maybe our surprising lack of uniqueness in the cosmos.
And that, I think, is why it's so captivating, why it keeps us coming back. It's not just about aliens. It's fundamentally about us. It confronts our assumptions about ourselves.
Okay, so our mission for this deep dive then. We're going to unpack this cosmic enigma, piece by fascinating piece. We'll explore its surprising origins, how this massive question started almost casually.
We're at lunchtime chat, essentially.
Then we'll dive into the powerful, almost inescapable reasons we expect to find company out there among the stars. The statistics, the logic.
Why the silence feels so wrong, based on what we know.
After that, we'll dive headfirst into the myriad of proposed explanations for that deafening silence. And there are a lot of them.
Everything from, cosmic rarity, the idea that we're incredibly special.
To some pretty chilling interstellar politics, maybe.
Oh, definitely. Some unsettling possibilities there.
And finally, we'll grapple with the profound philosophical and existential implications this whole mystery holds for humanity's future.
Because, as you said, this isn't just some abstract academic question. It might actually define our destiny, depending on the answer.
So settle in, everyone. We're about to explore maybe the biggest question there is. Where is everybody? Okay, let's really start unpacking the core of this enigma, this contradiction. It all begins with those astonishing statistics, right? The numbers that fuel the expectation.
That's the foundation. At its heart, it's this stark contrast. On one side, the immense statistical likelihood that extraterrestrial civilizations should exist.
Just thinking of the scale, our own Milky Way galaxy. Estimates vary, but what are we talking? 100 billion to 400 billion stars.
That's the ballpark, yeah. A truly mind-boggling number. And remember, that's just our galaxy.
Right, one galaxy among potentially billions in the observable universe.
Exactly. The total number of stars is almost beyond meaningful comprehension.
And we now believe that most of those stars, maybe nearly all of them, host planets. Planets capable, potentially, of supporting life.
Not just that, but our galaxy is ancient. billions of years old,
Mhm.
way older than our solar system.
So there's been ample time, vast stretches of cosmic time for life to emerge, to evolve, for intelligence to develop somewhere else.
Given all of that, the number of stars, the number of planets, the sheer age, it really does feel statistically inevitable that we should have encountered some evidence by now.
Like a radio signal. Or maybe even, some kind of probe or artifact. Something.
Something, yes. This argument of probability is really the cornerstone of the paradox. It's built on the idea that if the conditions for life are as, let's say, permissive as Earth's history suggests.
Meaning life got started here relatively quickly.
Right. If that's typical, then extraterrestrial life should be common enough that we'd have detected it by now.
So the paradox isn't just, weird, no signals yet. It forces a much deeper question.
It forces us to ask, is our understanding of life's prevalence fundamentally flawed? Are we overestimating how easy it is for life to start or evolve intelligence?
Or are there significant barriers we don't know about? Things that stop life or civilizations from developing or becoming detectable.
Precisely. And that's where it challenges those core scientific assumptions, like the Copernican principle you mentioned earlier, the idea that we're not special.
If Earth isn't unique, and the laws of physics and chemistry are universal,
And if life popped up here fairly early on, geologically speaking, within maybe the first billion years?
then logically, shouldn't that same progression have happened elsewhere? Many, many times over cosmic history.
That's the crux of it. The paradox forces a critical reevaluation. Either our understanding of abiogenesis, the origin of life, is incomplete,
Or maybe the evolution of complex intelligence is the real hurdle.
or there are these significant, as yet unknown barriers. Great filters, as we'll discuss, stopping civilizations in their tracks.
And that's what elevates it, isn't it? From just a puzzle, where are the aliens, to this profound philosophical and scientific dilemma.
Exactly. It's not just about them. It forces us to question us, our place, our uniqueness, or maybe our profound lack of uniqueness. What does their absence tell us about our own prospects? That's why it's so endlessly fascinating.
Okay, so this huge question, where is everybody? It actually has a surprisingly informal origin story. It wasn't some big formal paper initially.
Not at all. It bears the name of the brilliant Italian physicist Enrico Fermi, and the story goes it happened during a lunch conversation. Yep, back in 1950 at Los Alamos National Laboratory, Fermi was there with colleagues Emil Konopinski, Edward Teller, Herbert York, all big names in physics.
And Fermi, he was known for this, right?
Yeah.
Asking these deep, almost startling questions.
Yeah.
And doing quick calculations in his head.
He had a real knack for it, a penchant for posing these seemingly simple questions that cut right to the heart of complex problems, and for doing these back-of-the-envelope calculations.
So what happened at lunch?
Well, apparently they were chatting about a recent cartoon in the New Yorker magazine, something about flying saucers and aliens stealing trash cans, I think.
Okay. Standard lunchtime chat for physicists.
Maybe. Anyway, the conversation drifted to the possibility of extraterrestrial life and interstellar travel. And Fermi, reportedly, just started doing some quick, rough calculations right there.
Like how many stars, how many planets.
Exactly. Based on the estimated number of stars, the likely number of planets, the age of the galaxy, he figured that if alien life was common and if interstellar travel was feasible, even at slow speeds, then Earth should have been visited by now. Not just once, but probably many times over its long history. He famously blurted out, "But where is everybody?"
Wow. So a casual question over lunch, sparked by a cartoon, leads to one of the biggest paradoxes in science.
It's quite remarkable, isn't it, how that spontaneous query could trigger such a cascade of scientific thought and speculation that, continues full force today.
Did Fermi ever write about it formally?
No, he never published anything formal on the specific paradox. But the question stuck with his colleagues. It circulated informally. It just resonated.
So when did it become more, official?
The first time it really appeared in print in a serious scientific context was in a 1963 paper by none other than Carl Sagan.
Ah, Sagan. Makes sense.
But it was Michael H. Hart who really formalized it in a very influential 1975 paper. Its title was pretty blunt: An Explanation for the Absence of Extraterrestrials on Earth.
And what was his explanation?
His conclusion was stark. He argued, after analyzing various possibilities, that the lack of evidence meant we are the first civilization in our galaxy.
Whoa, that's a bold claim. The first.
Extremely bold. It really threw down the gauntlet. Hart's work was crucial because he moved it from Fermi's informal query to a structured scientific problem. He meticulously characterized the paradox.
How did he structure it?
He categorized the potential solutions into four broad types. First, physical limitations. Maybe interstellar travel is just impossible or impractical.
Okay, the universe is too big, the speed limit too slow.
Second, sociological choices. Maybe advanced civilizations just aren't interested in exploration or contact. They stay home or they hide.
The zoo hypothesis kind of thing.
Potentially, yeah. Third, temporal factors. Maybe civilizations existed long ago and died out, or they'll only emerge far in the future. We're just missing them in time.
The timing is off.
And fourth, the inherent nature of extraterrestrial beings. Maybe they're just fundamentally different from us in ways we can't predict or detect.
That's a really useful framework. And then someone else built on that, Tipler.
Right. Frank Tipler, in 1981, he introduced what's often called the Hart-Tipler conjecture. And this brings in the concept of von Neumann probes.
Von Neumann probes.
Yeah.
Self-replicating spacecraft, right? Like cosmic viruses.
Sort of, yeah. Imagine a highly advanced robotic probe that travels to another star system. It lands on an asteroid or a moon, uses the local resources to build copies of itself.
And those copies then launch to other star systems, repeating the process. Exponential growth.
Exactly. Tipler argued that even one such civilization, launching these probes, could explore and effectively colonize the entire Milky Way galaxy in just a few million years.
Which sounds like a long time to us, but cosmically, it's nothing, a blink of an eye.
Precisely. So Tipler's point was, if intelligent life had arisen elsewhere and developed this kind of technology, these probes should be everywhere by now, including here in our own solar system.
But we don't see any evidence of them. No self-replicating alien machines mining the asteroid belt.
Correct. So Tipler argued their non-detection is powerful contrapositive evidence. The fact we don't see them strongly implies that no intelligent life capable of building them exists beyond our solar system.
That really strengthens the paradox, doesn't it? It moves beyond just listening for signals to looking for physical artifacts.
It does. It further solidified the paradox as a major scientific problem, not just a philosophical musing.
It's just amazing how it evolved. From Fermi's lunch chat to Hart's categories to Tipler's self-replicating probes. It shows how science can take a simple, nagging question and build these elaborate frameworks around it.
And it taps into such a deep human curiosity, doesn't it? This question about are we alone? It's not new. People were thinking about other worlds centuries ago.
Like Bernard of Bouvier de Fontenelle in the 1600s or Jules Verne dreaming of space travel. We've always wondered.
Absolutely. And that enduring fascination is why the Fermi Paradox remains one of the most profound unanswered questions in astrobiology. It's absolutely central to SETI research, the search for extraterrestrial intelligence.
It forces us to think deeply, not just about aliens, but about ourselves, our place, the nature of intelligence itself, the limits of exploration.
And critically, it challenges our anthropocentric viewpoint, our tendency to assume aliens would think and act like us.
Aye, we're looking for signals we would send or probes we would build. But what if they operate on completely different principles, use technologies we can't even imagine?
That's a huge part of the mystery. This paradox isn't just about astronomy or biology. It weaves together sociology, philosophy, even questions about existential risk. It's this uniquely powerful scientific puzzle.
And just trying to solve it, even thinking about the possibilities, pushes the boundaries of our understanding. It forces us to confront our assumptions.
It forces us to step outside our very human perspective and try, however imperfectly, to imagine the truly alien. That's a profound intellectual challenge.
Okay, so let's dig into why we expect to find someone. What's the basis for this strong expectation of company? It really starts with the scale, doesn't it? Numbers that are just hard to fathom.
Absolutely. The sheer, incomprehensible scale of the universe is the first pillar. Let's just focus on our own Milky Way galaxy for a moment.
Okay, we said maybe 100 billion to 400 billion stars. Let's just say a couple hundred billion, to be conservative.
Couple 100 billion suns, yes. And that's just one galaxy. Now, multiply that by the estimated number of galaxies in the observable universe. Current estimates are hovering around 2 trillion galaxies.
2 trillion galaxies, each with potentially hundreds of billions of stars.
Do the math. It's something like 70 sextillion stars. That's a 7 followed by 22 zeros.
76 trillion. I can't even visualize that. Is that more stars than grains of sand on Earth?
Considerably more, yes. It's a number that almost loses meaning. It's so vast. The sheer scale is 0.1.
0.2 must be planets, right? Stars are great, but you need worlds.
Exactly. And this is where recent astronomy, especially missions like the Kepler Space Telescope, has been revolutionary. We used to speculate about planets outside our solar system. Now we know.
And we know they're not rare, they're common.
Incredibly common. The data suggests that virtually every star in the galaxy hosts at least one planet. Maybe more.
So the number of planets likely far exceeds the number of stars.
That's the implication. We're not talking about a few potential homes for life scattered across the void. We're talking about a cosmic ocean absolutely filled with planets. Trillions upon trillions of them in our galaxy alone.
Okay, vast numbers of stars, even vaster numbers of planets. What's the next piece?
Time. Cosmic time. A significant proportion of these stars, and therefore their planets, are much, much older than our own sun and solar system.
How much older?
Billions of years older. Our sun is about 4.6 billion years old, relatively middle-aged for a star like it. There are stars out there that are 8, 10, maybe even 12 billion years old.
So if life takes time to evolve intelligence, those older systems had a huge head start.
A massive head start. Billions of years more time for life to emerge, for it to evolve complexity, for intelligence to potentially arise and develop technology, maybe even expand.
So if you put it all together, the immense number of stars, the ubiquity of planets, and the vast stretches of time available,
it creates this almost inescapable probabilistic argument for the widespread presence of life, including intelligent life.
even if the chances on any one planet are tiny.
Multiply that tiny chance by the sheer number of opportunities over billions of years, and the absolute number of advanced civilizations should still be immense. Potentially millions, maybe billions, just in our own galaxy over its history.
And that's what makes the observed silence so deeply perplexing. The universe should be noisy, statistically speaking.
This argument of probability is really the engine driving the paradox. It hinges on the idea that if Earth's conditions and history are reasonably typical,
Life should be common enough that we'd have seen something by now.
it's a very logical, almost mathematical expectation based on what we see around us and our understanding of the universe's scale and age.
And this expectation extends beyond just life existing to intelligent life doing things, right? Like expanding.
Yes, the argument often includes a projection of certain tendencies, particularly those observed in humanity, onto potential alien civilizations.
Like our drive to overcome scarcity, find new resources, new energy, colonize new places.
Exactly. The thinking goes, if an intelligent species arises, it will likely develop technology to solve problems, manage resources, and eventually, perhaps inevitably, look beyond its home world. At least some of them would.
And they'd spread out, like those theoretical models suggesting the Milky Way could be colonized relatively quickly.
Right. Models suggest that even with relatively slow sublight speed travel, a single expanding civilization could traverse and potentially colonize the entire galaxy within, say, 5 to 50 million years.
Again, sounds long to us, but on a galactic timescale, that's very fast. The galaxy should be full by now if anyone started early.
This is where it gets really interesting, though, because we hit a key tension.
Which is?
Projecting our drives, our curiosity, our tendency to expand, our perhaps historically colonial impulses onto hypothetical aliens. That's a potentially flawed anthropocentric assumption.
We're assuming they'd want to colonize the galaxy, just because maybe we would.
Precisely. What if their motivations are completely different? What if their evolutionary path led to different priorities? Maybe large-scale physical expansion isn't a universal goal for intelligence.
So their tendency to colonize might just not exist. Or maybe they expand in ways we can't recognize, like into virtual realities or something.
Exactly. So the paradox is built, in part, on this human logic, this projection of ourselves onto the cosmos. But the silence itself might be telling us that alien behavior, alien motivations, are fundamentally different. They might not play by our expected rules.
Okay, so trying to quantify these odds, to put some structure around these factors, that's where the Drake equation comes in.
Yes, astronomer Frank Drake developed it back in 1961, actually for the first SETI meeting. It's famous. N, R times FP, times nu times phi times FC times L.
N being the number of civilizations in our galaxy we could potentially communicate with right now.
Correct. But it's crucial to understand its purpose. It wasn't really designed to give a precise numerical answer. Its real value is as a conceptual framework.
How so?
It forces us to break down this huge question, how many aliens are out there? into a series of smaller, more manageable factors. It delineates the key astrophysical, biological, and sociological hurdles that need to be cleared for a communicative civilization to exist.
It maps out the unknowns.
Exactly. Let's quickly break down those terms because it really shows where the uncertainties lie.
Okay, our star.
Are the rate of formation of stars suitable for life in our galaxy? Current estimates are somewhere between, say, 1 and 10 suitable stars forming per year. That seems reasonably well known.
Okay, next is FP, fraction of those stars with planets.
And thanks to Kepler and other exoplanet hunters, we now think FP is close to 1. Basically, planets are everywhere. That term is much less uncertain than it used to be.
Good news for life, potentially. Then next.
Fen is the average number of planets per star system that could potentially support life. Basically, the number of habitable worlds. Estimates here vary, maybe 0.5 to 3 per system.
But habitable is getting more complex, right? You mentioned plate tectonics earlier.
Exactly. This is where recent research adds fascinating nuance. It's not just about being in the habitable zone for liquid water. Factors like having long-lived plate tectonics, a good mix of continents and oceans, these seem critical for the long-term stability and nutrient cycling needed for complex, intelligent life.
So the number of planets suitable for intelligent life might be much smaller than the number suitable for any life.
Very likely, yes. This refinement significantly impacts the NA term, or maybe pushes the complexity into the later terms.
Okay, what are the later terms?
FLL. FLL, the fraction of those suitable planets where life actually arises, and biogenesis. Life appeared pretty quickly on Earth, which might suggest FLL is high, but we only have one data point Earth. It's still a huge unknown. Is life easy to start, or was Earth incredibly lucky?
Right, the ultimate origin question.
Right.
Then fifth.
Phi, the fraction of planets with life where intelligent life evolves. This is one of the biggest uncertainties. Drake guessed maybe 1%.
But based on Earth, only one species, us, developed technology out of millions, and considering those stricter requirements like plate tectonics.
Some recent work suggests Phi could be vastly smaller, maybe 500 times smaller than Drake's initial guess, or even more. Maybe intelligence like ours is exceptionally rare, even if simple life isn't.
That's a major potential filter right there. Next is FOC.
FC, the fraction of intelligent civilizations that develop technology that releases detectable signs into space, like radio waves, lasers, maybe huge structures. Do they choose to be detectable? Do they develop tech we can even recognize? Another big unknown.
And finally, L.
L, the average length of time such civilizations release detectable signals, their communicative lifespan. This is arguably the most uncertain and the most impactful term.
How long does a technological civilization typically last before it goes quiet, either through destruction or maybe just changing its technology?
Exactly. Does it last a few hundred years? A few thousand? Millions? Billions? The value of L drastically changes the final calculation for N. If L is typically short, say only a few centuries.
Then even if civilizations are constantly popping up, the chance of one being active right now and close enough for us to detect is tiny. They'd be like brief fireflies blinking in the cosmic night.
Precisely. So you see, the Drake equation's value isn't in giving us n of 5 or n equals 10 million, because the uncertainties in FL, Phi, FC, and especially L are so immense, n can vary by 10 orders of magnitude or more.
So it's not a prediction machine.
Not at all. It's a diagnostic tool, a powerful heuristic. It structures our ignorance, highlights the key scientific unknowns, and guides where we need more research. The problem isn't the equation, it's the vast uncertainty in its parameters.
It tells us what questions we need to answer.
Exactly. It maps out the challenge.
Okay, another framework often discussed alongside this is the Kardashev scale. This one tries to classify civilizations based on energy use.
That's right. Proposed by Soviet astrophysicist Nikolai Kardashev in 1964. He developed it specifically to help guide SETI research, thinking that more advanced civilizations would inevitably harness and utilize vast amounts of energy, and some of that energy use might be detectable.
So it benchmarks technological advancement by energy consumption. What are the levels?
Kardashev defined 3 main types.
Type I.
Type I is a planetary civilization. It can harness and utilize all the energy available on its home planet that reaches it from its parent star. For Earth, that's roughly 2 times 10 to the 17 watts.
And where are we now?
We're currently considered a Type 0 civilization. By 2020, our total energy consumption was around 2 times 10 to the 13 watts. So we're still several orders of magnitude away from Type 1.
What would a Type I civilization look like? What could they do?
Think global-scale energy projects, maybe planetary fusion power grids, antimatter reactors, continent-spanning solar arrays, maybe even controlling the weather, large-scale terraforming, full mastery of planetary energy resources.
Okay, then type 2.
Type 2 is a stellar civilization, much more advanced. It can harness the entire energy output of its host star. We're talking about 4 times 10 to the 26 watts for a sun-like star. A colossal amount of energy.
How would a civilization even do that?
The most famous theoretical concept is a Dyson sphere, or maybe a Dyson swarm, a vast megastructure or collection of structures that completely or partially encircles the star to capture its energy.
Like building a shell around the sun.
Essentially, yes.
Sure.
A Type 2 civilization could potentially power computations or projects on an unimaginable scale and transmit information across huge interstellar distances. Their energy signature would be enormous.
And type 3?
Type 3 is a galactic civilization, the highest level Kardashev originally proposed. This civilization harnesses the energy output of its entire host galaxy. That's roughly 4 times 10 to the 37 watts.
Controlling the energy of billions of stars. That's almost godlike.
It implies technology and engineering on a scale that's difficult for us to even conceive. Manipulating stars, perhaps moving them. Their presence would likely alter the visible structure of their entire galaxy. They could transmit vast libraries of information across intergalactic space in seconds.
Have people proposed types beyond 3?
Yes, there have been extensions, Type 4 harnessing galaxy clusters, Type V the whole universe, even Type 0 for us. Kardashev himself estimated that humanity, assuming a steady 1% annual growth in energy use, might reach Type Y in a few centuries, Type 2 in around 300 years, and Type 3 in about 5,800 years.
Which, again, on a cosmic timescale is incredibly fast. If intelligence isn't unique to Earth, there should have been plenty of time for others to reach these levels long before us.
And that is the Kardashev scale's direct relevance to the Fermi Paradox. It gives SETI researchers specific high-energy techno-signatures to look for.
Observable evidence of advanced technology.
Right. The theoretical existence of even one Type 2 or Type 3 civilization anywhere in our observable vicinity implies their energy consumption and activities would be so immense they should be highly detectable.
Their waste heat alone should light up infrared telescopes, right?
Right.
Or the shadows of their megastructures should block starlight in predictable ways.
Exactly. So the fact that we don't see unambiguous evidence of these large-scale engineering projects, no obvious Dyson spheres, no galaxies visibly manipulated by superintelligences, this absence constitutes a fundamental observational basis for the Fermi Paradox.
We have a scale for what extreme advancement might look like, energetically speaking, and the universe seems conspicuously devoid of it. It's the silence of the giants.
It is. But there's an important caveat here, too. The scale itself makes an implicit assumption.
Which is?
It assumes that advanced civilizations will inevitably follow this energy-intensive expansionist path, sort of mirroring humanity's historical trajectory and ambitions.
But what if they don't? What if they
Right.
choose a different path?
Exactly. What if advanced civilizations prioritize efficiency over raw power? Or perhaps they focus on engineering of the small, manipulating matter and energy at the quantum level rather than building enormous structures. Or maybe they transition to virtual existence, as we discussed.
If their path diverges from this energy-hungry model, the Kardashev scale might not be a useful guide for detecting them. They could be hyper-advanced, but invisible to us.
Precisely. It adds another layer of complexity. We might be looking for cosmic lighthouses when they're using undetectable quantum entanglement communicators, or living quiet lives inside planet-sized computers. Our assumptions shape what we look for.
Okay, so faced with this profound silence, despite the probabilities, people have proposed all sorts of explanations. Let's dive into those. You said they fall into roughly 3 categories.
Broadly speaking, yes. The first category tackles the possibility that life itself, or at least intelligent life, is just exceedingly rare. The silence isn't because they're hiding or dead, it's because they never existed in the first place, or hardly ever.
This implies the universe is largely sterile, or that intelligence like ours is an incredible fluke.
Right. This line of reasoning often involves the concept of the Great Filter, which we touched on earlier. It was popularized by economist Robin Hanson.
The Great Filter. Remind us what that is again.
It's a hypothetical barrier, or series of barriers, that is extremely difficult for life to overcome. It drastically limits the number of planets that end up hosting intelligent, spacefaring civilizations.
And if this filter lies in our past,
If it's somewhere between the origin of life and us sitting here talking about it, it means we somehow managed to pass through it. That makes our existence, human intelligence, incredibly rare. We're the lucky ones who slip through the net.
We're the exception, not the rule.
Exactly. And a prominent hypothesis that represents this past filter idea is the rare Earth hypothesis.
Put forward by Peter Ward and Donald Brownlee, right? Paleontologist and an astronomer.
That's them. In their book from 2000, they argued that while simple microbial life might be relatively common in the universe,
The specific conditions needed for complex life animals, plants, and especially technologically intelligent life are exceedingly rare. Earth is, well, a rare Earth.
they propose it requires an almost improbable confluence of factors, a long checklist of necessary conditions that all have to line up perfectly and stay stable for billions of years.
What's on that checklist? We mentioned a few earlier.
It's quite extensive. You need the right kind of star, stable, long-lived, like our G-type sun. You need to be in the right location in the galaxy, the galactic habitable zone, not too close to the danger center, not too far out in the sparse edges.
Okay, location, location, location.
You need a planet of the right mass with the right axial tilt for stable seasons, and a stable near-circular orbit within the star's habitable zone for liquid water.
That seems pretty standard for habitability discussions.
Yes, but then it gets more specific. They argue you need a large moon, like ours, to stabilize the planet's axial tilt over long timescales, preventing wild climate swings. Our moon also drives tides, which might have been crucial for early life moving on to land.
Ah, the moon is critical. What else?
A suitable atmosphere, of course, for protection and breathing, liquid water, oceans. But crucially, they emphasize the need for active plate tectonics and a magnetic iron core.
We talked about plate tectonics. Why is it so vital for complex, intelligent life specifically?
Well, as we discussed, long-lived plate tectonics acts like a planetary thermostat, regulating climate over geological time through the carbon cycle. It prevents runaway freezes or greenhouse effects.
It keeps things stable enough for billions of years of evolution.
Right. And it drives nutrient cycling, eroding rocks, delivering minerals to the oceans, which fuels biodiversity. It also creates diverse environments, mountains, coastlines, deep-sea vents, which pushes evolution through different pathways.
And the mix of lands and oceans.
Seems crucial, too. Oceans provide the initial crucible for life, but dry land appears necessary for the development of things like fire, complex tools, and, eventually, technology. You need both.
And the magnetic core.
Generates a global magnetic field, which shields the atmosphere and surface life from harmful solar wind and cosmic radiation. Without it, the atmosphere might get stripped away and the surface bombarded.
So the rare Earth hypothesis basically says you need all of these things: the right star, galaxy location, planet size, orbit, large moon, plate tectonics, magnetic field, land-water mix, all perfectly aligned and stable for billions of years.
That's the argument. And the probability of getting that entire checklist right might be vanishingly small, making planets capable of hosting complex, intelligent life incredibly rare.
If that's true, then humanity might indeed be a cosmic anomaly, a profound exception, challenging that Copernican principle of mediocrity.
And there's some empirical support right here on Earth, isn't there? Billions of years of life, countless species.
The only one, Homo sapiens, developed radio telescopes and starships, in theory, and only in the last tiny fraction of Earth's history.
Exactly. Other intelligent creatures, dolphins, apes, octopuses, have existed for millions of years without building cities or launching rockets. This suggests that the jump from basic intelligence to technological civilization, that phi term in Drake's equation, might be the real great filter. Maybe intelligence is common, but technological intelligence is astronomically rare.
That's a sobering thought. The silence means we're either alone or among the very, very first. A powerful explanation for the quiet cosmos.
It certainly is. It places the biggest hurdle behind us.
Okay, but what if the great filter isn't in the past? What if the hardest part is still to come? This brings us to the second category of solutions, right?
Yes, and this one is considerably more ominous. This category suggests that advanced civilizations simply don't last very long. They reach a certain point and then they vanish.
Destroy themselves, perhaps.
That's the core idea. If the great filter lies in our future, it implies that the path ahead for any technological civilization is fraught with existential peril. The silence we observe isn't because life is rare, but because advanced life inevitably, or almost inevitably, self-destructs before it can become truly widespread or interstellar.
So the cosmic silence becomes a warning, a glimpse of our own potential fate.
Exactly. It transforms the Fermi Paradox from a curiosity into an urgent existential warning for human civilization itself. The quiet out there might be the sound of countless failed attempts, a cosmic graveyard.
That's genuinely terrifying. What are the proposed mechanisms for this self-destruction? What could this future filter be?
There are several candidates, unfortunately, many of which seem quite plausible given our own current trajectory.
Like nuclear war.
That's a classic one. As a species, we developed the technology for self-annihilation relatively early in our technological phase. Global conflict escalating with weapons of mass destruction remains a potent threat. An advanced civilization might reach a point where its power is simply too great for its wisdom or political structures to handle.
Okay, self-inflicted war. What else?
Environmental collapse. Unsustainable exploitation of resources, runaway climate change leading to ecological breakdown, mass famine, societal collapse. If a civilization can't manage its planetary impact, it might destroy the very foundation it needs to survive and progress, certainly preventing it from reaching Kardashev type I, let alone higher.
We're certainly grappling with that possibility right now.
We are, and then there are risks from future technologies. Uncontrolled artificial intelligence is a big one.
AI, how could that be a filter?
Well, imagine creating a superintelligence far beyond human capability. If its goals aren't perfectly aligned with ours, or if it optimizes for something in an unexpected and catastrophic way, it could pose an existential threat. Or perhaps competing AIs wage wars we can't even comprehend.
Or maybe advanced biotechnology. Designer pandemics, genetic manipulation gone wrong.
Precisely. Powerful technologies bring powerful risks. If civilizations typically fail to manage these risks responsibly, then maybe that's the great filter. Technology itself becomes the trap.
So, viewing the paradox through this lens, it's a direct call for us to get our act together, to address climate change, manage AI development responsibly, prevent global conflict.
It absolutely is. It suggests that reaching interstellar status requires not just intelligence, but profound wisdom, cooperation, and foresight qualities that might be exceedingly rare or difficult to sustain. Survival itself might be the hardest test.
And related to this idea of civilizations not lasting long, there's the cosmic blank problem too, right?
Right.
Even if they don't self-destruct completely.
Yes, this fits well within this category. Even if a civilization survives for, say, 10,000 or 100,000 years, their period of actively broadcasting detectable signals might be much shorter. That L term, again.
Like us with radio. We've only been loud for about a century.
Exactly, a mere cosmic blink. If that's typical, maybe civilizations quickly move to more efficient, less leaky communication methods like lasers or quantum entanglement, or they become concerned about attracting unwanted attention.
Then the window of time during which any given civilization is easily detectable via radio might be incredibly short.
Vanishingly short compared to the multi-billion-year history of the galaxy. So even if civilizations are popping up fairly often and lasting a decent while, the chances of two of them being in their brief loud phase at the same time and also being close enough to detect each other?
It becomes incredibly improbable. Like trying to see someone else's brief camera flash across a vast, dark ocean when they only flash it once every million years.
A perfect analogy. It's a profound temporal barrier. The haystack isn't just vast space, it's also vast time. This alone could explain a lot of the silence, without needing rare life or universal self-destruction.
Okay, so category 1. Life or intelligence is rare. Past filter. Category 2. Civilizations don't last long or aren't detectable for long. Future filter or short L. What's the third category?
The third broad category suggests that they are out there, possibly in large numbers and for long durations, but for various reasons we simply can't see or hear them. Or perhaps they choose not to be seen or heard.
So the problem isn't their existence, it's our detection capabilities or their intentions.
Exactly. This covers a wide range of possibilities. Let's start with our own technological limitations.
SETI's challenges. We've only been listening for 60-odd years with limited resources.
Right. Our searches haven't covered the whole sky or all possible frequencies or all possible signal types. We can't continuously monitor millions of stars for faint intermittent signals. It's prohibitively expensive and technically challenging. We mostly take brief snapshots.
And even if a signal arrives, we have to be looking at the right place at the right time with the right equipment tuned to the right frequency.
The number of coincidences required is enormous. And fundamentally, maybe they're not communicating using methods we'd even recognize.
Beyond radio waves or lasers?
Perhaps. Quantum communication, neutrino beams, gravitational waves, maybe something involving dark energy or dimensions we don't understand. If their physics is centuries or millennia ahead of ours, their communication might be completely invisible to us. They might be using hyper-efficient, targeted communication that doesn't broadcast wastefully in all directions.
So we have this inherent listening bias. We're looking for technologies similar to our own.
It's a strong possibility. We project our own technological evolution onto them. This means we might be fundamentally overlooking signals that are right under our noses simply because they don't fit our preconceived notions.
Which brings us back to that crucial point. Absence of evidence isn't evidence of absence.
Especially when the search space is so vast and our tools are still, relatively speaking, quite primitive. It's like an indigenous tribe in the Amazon listening for smoke signals and concluding there's no global internet because they don't detect any smoke. Our methods might be fundamentally inadequate for the task.
Okay, limitations on our end. What else falls into this category?
The sheer distance. Even if civilizations are common and communicative, they might just be too far away.
The cosmic distance problem.
Right. The Milky Way is 100,000 light years across. Even our nearest neighboring galaxy, Andromeda, is 2.5 million light years away. Communication is limited by the speed of light.
So a signal from the other side of our own galaxy takes 100,000 years to reach us. A conversation is impossible.
Absolutely. Real-time interaction is off the table for interstellar distances. And detecting a transient signal that started its journey millennia ago requires incredible luck. This inherent communication lag, imposed by physics itself, drastically reduces the likelihood of detection. Distance alone could be a huge factor in the silence.
We could just be too isolated in our corner of space and time.
It's a very real possibility. Now, beyond technological limits and distance, we get into the really intriguing sociological explanations. What if they exist? They could contact us, but they choose not to.
This is where we get ideas like the zoo hypothesis.
Exactly. A fascinating, if slightly unsettling idea. It speculates that advanced extraterrestrial civilizations know we're here, but they deliberately avoid contact.
Why would they do that?
The analogy is like a wildlife preserve or a zoo. They observe us, perhaps study us, but refrain from interfering to allow our natural development, our cultural evolution, to proceed without contamination.
A kind of prime directive, like in Star Trek, ethical non-interference.
That's the idea. It implies a universal cultural or legal policy among advanced civilizations. Maybe they see us as too primitive, too volatile, or maybe they have ethical rules against interfering with developing world until they reach a certain maturity level.
So the silence isn't absence or indifference.
Mm-hmm.
It's deliberate. Benevolence, maybe? Or just proof?
It could be seen that way. They're waiting for us to grow up, perhaps solve our own problems, achieve interstellar capability ourselves before they initiate contact. It suggests a level of cosmic governance or shared ethics we can only guess at.
Okay, that's one view. But then there's the polar opposite, the dark forest hypothesis.
Yes, popularized by Lou Sixon's sci-fi novel, The Dark Forest, this explanation is chilling.
How does it explain the silence?
It posits that, yes, many alien civilizations do exist, but the reason they're silent is because the universe is an incredibly dangerous place. It's a dark forest filled with unseen hunters.
Hunters, meaning other civilizations?
Yes. In this scenario, survival is the ultimate goal. Resources are finite. Intentions are fundamentally unknowable across the vast gulfs of space and culture. Trust is impossible.
So if you reveal your location...
Yeah, you immediately become a potential target.
Yeah.
Any other civilization, assuming the worst, might see you as a future threat or competitor for resources. The safest strategy, the only rational strategy in such a universe, is to remain hidden and silent. And if you do detect someone else...
you eliminate them before they can eliminate you. Shoot first. Ask questions later.
That's the terrifying logic of the dark forest. Silence is survival. Broadcasting your existence is like shouting in a forest full of predators, an existential mistake.
So the silence isn't empty. It's a tense, fearful quiet maintained by everyone who understands the danger.
It implies that the universe might be teeming with civilizations, but they are all desperately trying to avoid detection. And this has huge implications for our own efforts, like maybe actively messaging extraterrestrials.
Broadcasting our existence could be like painting a giant target on Earth.
If the dark forest hypothesis holds any truth, yes, it makes Métis seem incredibly reckless.
Wow. That's a stark contrast to the zoo hypothesis. From benevolent guardians to paranoid snipers. What other sociological ideas are there? Maybe they just don't care about expansion.
That's another line of thought. Maybe the assumption that intelligence inevitably leads to expansion and colonization is wrong. Perhaps many advanced civilizations reach a point of stability or sustainability where they have no desire to spread further.
They're content in their own star system. Or maybe they focus inward.
Exactly. Perhaps they develop incredibly rich simulated realities, virtual worlds, and prefer to explore inner space rather than outer space. The transcension hypothesis suggests something like this.
Transcension.
The idea that advanced civilizations eventually transcend our familiar physical universe. They might upload their consciousnesses, merge into collective intelligences, or transition into purely computational substrates existing as information patterns in highly compressed spacetime or energy fields.
So they basically leave our plane of existence, becoming undetectable because they're playing a different game entirely.
That's one interpretation. Or consider the inner space hypothesis, especially if civilizations become post-biological based on artificial intelligence.
Machine intelligences might have different motivations than biological life, less drive to reproduce and expand physically.
Potentially, yes. Their goals might revolve around information processing, computation, solving abstract problems, creating complex internal simulations, things that don't necessarily require building Dyson spheres or colonizing galaxies. Their priorities might be utterly alien to our biologically driven imperatives.
So the silence could just be cosmic indifference. They're out there doing their own thing, and interacting with messy biologicals like us holds no interest.
It's a plausible, if slightly humbling, possibility. They might be post-physical, post-biological, operating on scales or dimensions, or with motivations that render them utterly irrelevant to our search and us irrelevant to them. The silence of profound difference.
Okay, so we have all these potential explanations. How are we actively trying to find the answer? That brings us to SETI, the search for extraterrestrial intelligence.
Right. SETI is the umbrella term for the scientific efforts focused specifically on finding empirical proof of intelligent beings elsewhere. Not just looking for microbes, but for signals or artifacts produced by technology.
And the main method has been listening for radio signals.
Historically, yes. That's been the primary approach. Using large, highly sensitive radio telescopes to basically eavesdrop on the cosmos, hoping to pick up an artificial signal.
Why radio?
Because radio waves travel at the speed of light, they can traverse vast interstellar distances, and they pass relatively easily through the gas and dust that fills space. Plus, we developed radio technology ourselves, so it seemed like a logical place to start. Back in 1959, physicists Philip Morrison and Giuseppe Cocconi even suggested a specific magic frequency to listen on, the 21-centimeter hydrogen line.
Why that frequency?
Because hydrogen is the most abundant element in the universe, and it naturally emits radio waves at that specific frequency, 1420.4 millihertz. The thinking was any scientifically literate civilization would recognize its significance and might use it as a standard hailing frequency, like a cosmic dial tone.
So the search started there, Project Ozma.
Exactly.
Nice.
Frank Drake led Project Ozma in 1960. It was the first dedicated SETI search using a radio telescope to listen towards two nearby sun-like stars, Epsilon Eridani and Tau Ceti, around the hydrogen line frequency.
Did they find anything?
No compelling signals, unfortunately. But it was groundbreaking. It proved the concept was feasible and paved the way for many subsequent, more powerful searches. Projects like Meta and Beta later expanded the search dramatically, monitoring millions, even hundreds of millions, of radio channels simultaneously.
And it's not just radio, right? They also look for other things.
Correct. There's also optical SETI, which searches for brief, powerful pulses of laser light. The idea is that lasers could be a very efficient way to send directed interstellar messages. So searches look for light signals that are monochromatic, single color, and very brief, distinguishing them from natural astrophysical sources.
So after more than 60 years of searching, with increasingly sophisticated radio telescopes, optical detectors, massive computing power analyzing the data, what's the status?
The status is still silence. Despite decades of effort and significant technological improvements, no confirmed, unambiguous evidence of an extraterrestrial technological signal has ever been found.
Has SETI ruled anything out?
Well, the searches around the 21-centimeter hydrogen line have been extensive enough that we can probably say there aren't legions of civilizations blasting powerful, obvious signals at us on that specific frequency across the entire sky. Widespread, easily detectable emissions like that seem unlikely, at least nearby.
But the limitations are still huge.
Immense. As we've said, humanity has only been listening for a cosmic blink. Our best telescopes still struggle to detect faint signals from very far away. We can't monitor billions of stars continuously across all frequencies. The search space, all the stars, all the frequencies, all the signal types, all the time is unbelievably vast.
And a signal needs to be aimed at us, arriving when we happen to be looking.
The odds remain challenging. Our current technology, powerful as it seems to us, is likely still quite primitive compared to what might be needed or compared to what truly advanced civilizations might use.
Which brings us back again to that critical distinction.
Absence of evidence is not evidence of absence. Current SETI efforts are incredibly valuable, pushing the boundaries of technology and our understanding. But concluding they're not there, based on the current lack of detection, is premature.
It's like dipping that glass in the ocean.
Precisely. We've barely scratched the surface, and the search itself is still largely shaped by our anthropocentric assumptions looking for signals we know how to generate or detect. If they communicate using physics we haven't discovered yet, we'd miss it entirely.
Okay, so SETI is listening. But then there's METI, which is about shouting.
Essentially, yes. METI stands for Messaging Extraterrestrial Intelligence. Unlike SETI's passive listening, METI involves the active creation and transmission of interstellar messages from Earth, directed towards potentially habitable star systems.
We're trying to initiate the conversation.
That's the goal. Organizations like METI International, founded in 2015, are doing this. They've already sent transmissions containing scientific and mathematical information towards nearby stars like Leighton Star. The famous Arecibo message sent in 1974 was also a form of METI.
But this is controversial, isn't it? Active SETI.
Highly controversial. It sparks intense debate within the scientific community and beyond.
Because of the potential risks.
Exactly. The core of the debate revolves around whether actively advertising humanity's existence and location is wise, given that we know absolutely nothing about the nature or intentions of any potential extraterrestrial civilizations.
This is where the dark forest hypothesis comes back to bite us.
It looms large over the METI debate. If the universe is potentially hostile, if the dark forest logic holds, then METI could be an act of unimaginable recklessness. We might be attracting attention we really don't want, inviting preemptive destruction.
It turns the paradox into a potentially life-or-death gamble for our entire species.
It does. It's a profound ethical dilemma with potentially irreversible consequences. On the other side, proponents of METI argue the risks are overstated.
How so?
They might argue that any civilization capable of detecting our transmissions and reaching us to do harm would likely already know we're here from our unintentional radio leakage over the last century. Or they argue the benefits of potential contact, gaining knowledge, ending isolation outweigh the hypothetical risks. Some argue that silence itself is a risk, preventing potentially beneficial contact.
But without any data on alien motivations, are they likely to be peaceful explorers, indifferent observers, or hostile conquerors? Any decision about METI is basically a shot in the dark.
A profound gamble with humanity's future, yes. This debate is a direct, practical manifestation of the philosophical weight of the Fermi Paradox. It forces us to confront not just, are they out there, but should we let them know we are here, and we have no consensus.
Okay, beyond the search efforts themselves, are there criticisms of how we even frame the paradox?
Yes, there are some deeper critiques. Some scholars suggest that Fermi's original question might have been misinterpreted over the years. They argue Fermi, being a pragmatic physicist, was primarily questioning the feasibility and likelihood of interstellar travel, given the physics involved. His "where is everybody?" might have been less about the absence of life and more a skeptical take on building starships and crossing light years. If travel is practically impossible, then of course they're not here, regardless of whether they exist.
So maybe the paradox is more about the difficulty of spaceflight than the rarity of life.
That's one perspective, suggesting the focus should be less on biology and sociology and more on the hard physics and economics of interstellar travel. Maybe the barrier isn't a great filter, but just the sheer prohibitive cost and difficulty of traversing space.
And we keep coming back to the absence of evidence fallacy.
Right. Robert Freitas and others have strongly criticized the leap from "we haven't found them yet" to "they probably don't exist." Given the vastness we're searching and the limitations of our search, that conclusion is logically unsound. Our search volume is minuscule compared to the whole haystack.
We just haven't looked hard enough or long enough or in the right ways yet.
It's a very strong argument. And then there's the challenge to the assumed universal drives. The paradox often implicitly assumes aliens would want to expand, colonize, communicate conspicuously, just like we imagine we might.
But maybe that's just us. projecting our own restless, noisy nature onto the cosmos.
Exactly. Maybe advanced civilizations typically prioritize sustainability, internal development, virtual existence, or adhere to non-interference ethics like the zoo hypothesis. If colonization isn't the norm, or if communication is subtle and targeted, then the premise that they should be obvious breaks down.
Even the Kardashev scale, useful as it is, has its critics.
Yes, its focus solely on energy consumption might be too narrow. It potentially overlooks civilizations that achieve complexity and longevity through efficiency, information processing, or modes of existence that don't involve harvesting entire stars. Maybe true advancement lies in subtlety, not brute force energy use.
So the paradox itself might be built on flawed or incomplete assumptions about how intelligence behaves or evolves.
That's a key criticism. It remains a powerful question, but we need to constantly examine the assumptions embedded within it. It's a dynamic puzzle, constantly shifting as we learn more and question our biases.
This whole discussion really forces us to confront some deep philosophical questions about our place in the cosmos, doesn't it?
Absolutely. The Fermi Paradox isn't just a scientific puzzle. It plunges us right into existential territory. That central question, where is everybody? It directly challenges our perception of humanity's significance.
If life is common, as the numbers suggest, then why are we seemingly alone? What makes us different? Or are we not different, just unheard?
It presents us with these two profound and potentially quite terrifying possibilities.
Possibility one. We really are alone, or at least functionally alone in our observable universe.
If that's the case, it bestows this immense, maybe even crushing responsibility upon us. We would be the sole known custodians of consciousness, of intelligence, perhaps of meaning itself in this vast cosmic ocean, the only ones to wonder about the stars.
The pressure would be enormous to survive, to cherish what we have.
Immense. On the other hand, possibility too. Other civilizations do exist, maybe many of them, but they remain undetected for whatever reason.
What does that imply about us?
It might imply that humanity is simply unremarkable. Just one of countless species that reached a certain level, maybe not even a particularly interesting one from a more advanced perspective. Or perhaps we're seen as primitive, volatile, maybe even dangerous.
Like ants on a cosmic picnic blanket, mostly ignored.
Or perhaps quarantined, as the zoo hypothesis suggests. Either way, it challenges our sense of cosmic importance. It forces us to ask, how advanced are we really? What are our limitations? What does the silence, interpreted this way, imply about our own future potential and cosmic standing?
It forces a kind of cosmic humility.
It really does. Reevaluating our significance is a core philosophical outcome of grappling with the paradox.
And the implications of the Great Filter, especially if it's ahead of us, are particularly stark for our future, aren't they?
Extremely stark. If the Great Filter, that barrier that stops civilizations, lies in our future, then the cosmic silence isn't just a mystery. It's an ominous warning sign.
It suggests that the path ahead is incredibly dangerous, that most civilizations that reach our current stage don't make it much further.
Precisely. It implies that civilization-ending threats are not just possibilities, but perhaps statistically likely outcomes for technological species. Humanity could be standing right on the brink of a potentially insurmountable obstacle.
And we discussed some of those potential future filters. They're not abstract sci-fi concepts.
Not at all. Nuclear war, runaway climate change and resource depletion, uncontrolled AI, catastrophic misuse of biotechnology like engineered pandemics. These are plausible existential risks that arise directly from our own technological advancement and societal structures.
Things we are actively dealing with or failing to deal with right now.
Exactly. So if the Great Filter is ahead, then taking proactive, serious steps to mitigate these existential risks becomes absolutely crucial. It's not just about improving our lives, it's about ensuring our very survival as a species capable of a long-term future.
It means prioritizing things like global cooperation, responsible technology development, AI safety, environmental sustainability. These become prerequisites for surviving long enough to potentially become an interstellar civilization.
Our ability to overcome these self-inflicted threats will literally determine whether we become another silent statistic in the cosmic graveyard or if we manage to navigate the filter. The paradox, seen this way, is a powerful call for urgent self-assessment and collective action. It links our cosmic future directly to our present choices.
And throughout this, we keep bumping up against our own biases. The anthropocentric lens. How much does that shape the entire paradox?
It's arguably one of the most fundamental philosophical implications. Our human-centered perspective pervades how we even formulate the question and imagine the possibilities.
The initial framing assumes advanced aliens would explore, colonize, communicate in ways we find logical or recognizable, using radio, building big things.
Right. We project our own history, our curiosity, our drives, even our flaws like colonial ambition, onto hypothetical beings who might have evolved in utterly different contexts with completely different values and biologies. This projection might be profoundly misleading our search.
Is that what's meant by the Fermi delusion?
That concept suggests exactly that. The paradox isn't necessarily a deep cosmic mystery, but perhaps a reflection of our own biased assumptions. Our belief in our own significance, our assumption that advanced intelligences would surely want to talk to us or follow paths similar to ours. Maybe that's the delusion.
Maybe from an outside perspective, humanity doesn't look that appealing.
It's a humbling thought. An advanced civilization observing Earth might see a species that's rapidly destabilizing its own biosphere, that invests heavily in weapons of mass destruction, that's prone to conflict. We might look like an unstable, potentially dangerous, great filter candidate ourselves.
Why would they want to engage with that? Especially if they prioritize stability or self-preservation.
Exactly. From their perspective, avoiding contact might be the most logical and prudent course of action. This view suggests the silence reflects cosmic indifference or maybe caution rather than cosmic absence.
So advanced civilizations, whether biological or post-biological AI, might simply have no reason or desire to interact with us. They're operating on different motives. Maybe they've transcended physical expansion entirely.
It's a strong possibility. Their existence might be based on principles or goals completely orthogonal to ours. In this sense, the Fermi Paradox serves as a powerful mirror, reflecting our own assumptions and limitations back at us. It urges us to constantly question our human-centric viewpoint and try to imagine the truly alien, even if it means accepting our potential cosmic irrelevance.
Okay, so where are we now? What's the current state of play in trying to understand this? Are new discoveries changing the picture?
Yes, things are definitely evolving, especially thanks to advancements in astronomy. The exoplanet revolution is a huge factor.
Finding thousands of planets, proving they're everywhere.
Right. The sheer number of confirmed exoplanets, especially from Kepler and now TESS, statistically proves that planets are ubiquitous. Nearly every star has them. This powerfully reinforces the probabilistic side of the paradox. The opportunities for life are definitely out there in staggering numbers.
But at the same time, our understanding of what makes a planet truly habitable for complex life is getting more refined.
Exactly. It's not just about liquid water anymore. As we discussed, the importance of factors like long-lived plate tectonics, the right mix of land and water, a stable magnetic field, these more specific geological and environmental conditions seem crucial for the kind of long-term stability needed for intelligence like ours to evolve.
So while the number of planets is vast, the number of truly Earth-like planets with all these features might be much lower.
That's what current research suggests. Incorporating these stricter requirements into the Drake equation tends to significantly reduce the estimated number of communicative civilizations, potentially by several orders of magnitude. It doesn't solve the paradox entirely, but it might lessen the contradiction by making complex technological life rarer than simple microbial life.
It makes the silence a bit more understandable, perhaps. What about our detection techniques? Are we getting better at looking for signs of life?
We are. There's a lot of progress in developing techniques to detect biosignatures.
Chemical fingerprints of life in exoplanet atmospheres.
Yes, looking for gases like oxygen, methane, or combinations of gases that are out of chemical equilibrium and might indicate biological processes. The James Webb Space Telescope is starting to give us unprecedented data on exoplanet atmospheres.
In future telescopes.
Future missions, like the proposed Habitable Worlds Observatory, aim to directly image Earth-like exoplanets and analyze their atmospheres in detail. They might even be able to detect oceans and continents. This could move the field from speculation towards actual empirical observation of potentially habitable worlds, helping us constrain those crucial NEM and FEL terms in the Drake equation.
So the debates continue across different fields.
Oh, absolutely. In astrobiology, the focus remains on refining those Drake parameters, debating the likelihood of abiogenesis, and understanding the conditions for complex life, especially with these new geological insights.
And in physics and cosmology.
Discussions there might involve the fundamental nature of the universe. Is it just too vast for practical interaction? Are there limitations in our understanding of physics that hide other possibilities? People explore more radical ideas too, like advanced entities, creating new universes, or using things like quantum entanglement for communication.
And the many debate rages on.
Very much so. The ethics of actively broadcasting versus passively listening, informed by possibilities like the dark forest, remains a profound and unresolved dilemma. It forces us to confront deep questions about risk, responsibility, and our place in the unknown.
So, looking ahead, what are the key directions for research?
Definitely continued advancements in exoplanet detection and characterization, finding more Earth-sized planets and habitable zones, and crucially, analyzing their atmospheres for biosignatures and maybe even technosignatures, signs of artificial pollutants or structures.
Evolving SETI searches, too.
Yes, exploring new frequencies, different signal types, using AI to analyze data for patterns humans might miss, trying to move beyond purely anthropocentric assumptions about what an alien signal might look like, building more sensitive telescopes, both radio and optical, and leveraging citizen science to help process the vast amounts of data.
And you mentioned the importance of studying existential risks.
Increasingly so. The future filter hypothesis makes understanding and mitigating risks to our own civilization paramount. Studying factors that contribute to long-term civilizational survival, that L term isn't just relevant to the paradox, it's crucial for humanity's own future. Learning how to become a long-lived, sustainable civilization might be the most important step we can take.
So, the quest to solve the Fermi Paradox isn't just about finding aliens.
Not at all. It's a quest that forces us to understand life's origins, the conditions for intelligence, the future of technology, the challenges of long-term survival, and ultimately humanity's own place and potential destiny in this vast universe. It pushes us to learn more about ourselves.
So as we wrap up this deep dive, it's clear the Fermi Paradox remains one of modern science's most compelling, most perplexing questions. It's this stark contradiction. The universe seems ripe for life, yet the cosmic neighborhood appears deserted. Enrico Fermi's simple question, where is everybody? It still echoes profoundly.
The reasons to expect company are powerful. The sheer scale of stars and planets, the vastness of cosmic time, the apparent ease with which life started on Earth. Frameworks like the Drake equation map out the factors, while the Kardashev scale gives us a mind-bending glimpse of what truly advanced civilizations might achieve, making their apparent absence even more puzzling.
But the proposed explanations for the silence paint a vast, sometimes unsettling landscape of possibilities. Maybe life, especially complex, intelligent life, needing conditions like plate tectonics, is incredibly rare. The Great Filter is behind us. Maybe civilizations inevitably self-destruct or become undetectable. The filter lies ahead, a warning to us. Or maybe they're out there but hidden, indifferent, or deliberately avoiding us, the zoo, the dark forest, or something stranger still.
Our search efforts, SETI, and the contentious METI, are ongoing attempts to pierce that silence, but they're hampered by immense challenges and our own inherent biases. The absence of evidence is not evidence of absence remains a crucial mantra. We've barely begun to look.
And perhaps the deepest insight from grappling with the paradox is the mirror it holds up to humanity. It forces us to confront our anthropocentrism, to question our assumptions about intelligence and progress, and to consider our own future trajectory and vulnerabilities.
The silence could mean we're uniquely precious, tragically doomed, or simply cosmically irrelevant. It might be a warning, a mystery reflecting our ignorance, or perhaps a prelude to a discovery that changes everything. We simply don't know yet.
But the quest continues. As science advances, with new telescopes probing distant atmospheres and new ideas challenging old assumptions, we chip away at the edges of this enigma. A definitive answer might remain elusive for a long time, maybe forever, but the enduring mystery itself is invaluable.
It truly is. It's a powerful catalyst, driving scientific exploration, sparking philosophical contemplation, and ultimately deepening our understanding of our own cosmic journey. The search for everybody is, in a very real sense, a search to understand ourselves and our place in this vast, silent, and utterly fascinating universe.